Hey everybody. Today we're doing some harder improper integrals. Here's the three that we're going to tackle. Number one is the integral from negative infinity to 0, x e to the x dx. This is a type 1 improper integral. We've got a region of integration that goes on forever to the left. So instead of integrating from negative infinity to 0, we're going to integrate from L to 0, where we imagine L is some large negative number, and then let L go to negative infinity. Now we've got a proper integral there from L to 0. This is a prototypical integration by parts. We let u equal x, dv equals e to the x dx, differentiate u, anti-differentiate dv, and plug into the formula integral of u dv equals uv minus the integral of v du. Integrating e to the x, we just get e to the x. Here we've shown that x e to the x minus e to the x is an antiderivative of x e to the x. We then use the limits of integration, plug in 0, plug in L, and simplify a tiny bit. Now we just have to evaluate the limit. First part's easy. The limit as L goes to negative infinity of negative 1 is negative 1. The L e to the L is more complicated. That's a 0 times infinity indeterminate form. And so we're going to have to do a little work to actually evaluate that. Let's separate it out so that we don't have to deal with that negative 1 at the same time. The way we deal with a 0 times infinity form is by putting one of the factors in the denominator. So I'm going to take that e to the L, put it in the denominator, and make it e to the negative L. Now I've got an infinity over infinity form. L'Hopital's rule, differentiate the top, differentiate the bottom, and now, as L goes to negative infinity, the denominator goes to infinity, so this whole limit is 0. Putting everything together, the integral from negative infinity to 1, x e to the x dx, is just this limit that we got on the previous slide, and we know that L e to the L is going to 0, so overall we just get negative 1. Problem 2. Integral from 1 to 5, 1 over x minus 4 squared dx. This one's tricky. You have to notice that there's a vertical asymptote at x equals 4, which is smack dab in the middle of the region of integration from 1 to 5. If you just charge ahead and do a second fundamental theorem of calculus, getting an antiderivative and plugging in those endpoints, you will get the wrong answer. Instead, we have to break this integral up into two pieces in order to avoid that vertical asymptote. We're going to integrate from 1 to 4 and then do that as a limit from 1 to L as L goes to 4 from the left. And then we're going to integrate from 4 to 5 and do that as a limit as R goes to 4 from the right, integral R to 5, 1 over x minus 4 squared dx. So we really have two very similar integrals to evaluate here and then two limits. Let's look at the first one. Limit as L goes to 4 from the left, 1 to L, 1 over x minus 4 squared dx. The antiderivative is pretty easy. Negative x minus 4 to the negative first, plug in L, plug in 1, and then take the limit. Let L go to 4 from the left. Here, we're going to get a 1 over 0, so this is going to diverge. We get positive infinity. Now, we don't need to actually look at the right-hand part. We've discovered that this shaded area here on the left, the integral from 1 to 4, is not finite. And therefore, the whole integral, the whole area, has to be infinite as well. The rule is that if an improper integral diverges on a subinterval, like this, then it has to diverge on the whole interval. In other words, we aren't going to allow one infinity ever to cancel out another. Here, we can stop and just say that the integral diverges. Problem 3. Integral from negative infinity to infinity, x to the 5th minus x to the 3rd dx. So again, this is an infinite region of integration. This time, however, the region is infinite in both directions. Much like in problem 2, we have to break this integral up into two pieces and have two separate limits. So instead of integrating from negative infinity to positive infinity, we're going to do it from negative infinity to 0, and then from 0 to infinity, and then view each of those infinities with a separate limit, like I've got written here. So now each of those integrals is proper. We can just do a second fundamental theorem of calculus, get antiderivatives, plug in the endpoints, and then think about evaluating those limits. They both diverge in this case. So in that first case, when you have L going to negative infinity, you can, for example, factor out x to the fourth, and then you've got a product where both factors are going to positive infinity. So if you have even one of these two diverging, then the whole integral has to diverge by that rule we mentioned on the previous slide. That if improper integral diverges on a subinterval, then the whole thing has to diverge. So overall, the integral from negative infinity x to the fifth minus x to the third dx does not exist. Once again, you have to do two separate limits when you have an integral like this. You can't just do a limit as L goes to infinity from negative L to L. A picture makes this clear. The shaded region on the right is infinite, and the shaded region on the left is infinite. So we want to say that this integral from negative infinity to infinity f of x dx does not have a finite value. And yet, if you were to integrate it from negative L to L, just by symmetry, you would always get 0, an answer that just doesn't really make sense to us.